right, I'm going to get this started with our introduction slides, and then we'll shortly get to Edgar's talk. Thank you all for coming today. This is the monthly PCAST talk on behalf of the PRIMA community, which features science and technology talks on things related to infrared astronomy in general, but also future topics that would be very relevant for the PRIMA mission. A little bit of news. We are asking group members in our working groups and also just people from the larger community to tell us why they are looking forward to the PRIMA mission. We are hoping to feature these responses on social media and also importantly at the site visit that is a huge component of the committee review and selection process this spring. I posted this link in the chat. And I will repost again if it is not there. But if you have a second, please take some time to fill it out. It's enormously helpful for PRIMA. Also, please join us at JWST in January. We're hosting a PRIMA special session at the Winter JWST. This is in Phoenix, January 4th to 8th. And we are currently accepting contributed poster abstracts. Those are due on October 6th. And also, submitting to a special session does not limit your ability to submit to additional research talks on like other topics. So this is something that you could do in addition to whatever else you're planning on doing in WS, and it would be great for fostering participation in the PRIMA community, demonstrating interest, all those great things. A few things to add to your calendar. We have some upcoming talks. Our next PCAST on November 17th. By Kasia Dukowska from Leiden, and then on January 26th, Meredith McGregor from JHU. So make sure to check those out. And I will stop taking up your time and pass this along to Edgar Vidal. Edgar is a second-year graduate student at Tufts University, working with Dr. Anna Sajina, and he'll be presenting to us today on a paper actually that was just posted on the archive this morning, if you were looking carefully, on modeling the JWST MIRI populations, including dust-obscured AGN. So I'm going to stop sharing my screen and pass this off to Edgar, and you can feel free to take it away.
Cool. All right, let me just share my screen real quick. All right, great. So yeah, my name is Edgar. I am a second-year astrophysics PhD student studying at Tufts University. And like Jed McHading said, I'm going to be discussing how we've been modeling the JWST MIRI populations, including dust-obscured AGN. And so the outline for today's begin with a brief introduction, and we'll outline some of the necessary information that's needed for the talk. After that, I'll talk about some of the current modeling approaches that are trying to reproduce the JWST MIRI number counts. And then I'll introduce the FIRESIDE project and discuss some of the efforts that we're doing for the far infrared community. And then I'll talk about my recent work that just came out on the archive this morning on updating the STDs and incorporating AGN into the pySIDES semi-empirical framework. And lastly, I'll close up on how we can adapt our modeling framework for the far infrared and PRIMA community. And so I'd like to start off with the very familiar image of a galaxy seen through Hubble Space Telescope. And the most obvious features are the spiral arms and the stars that reside inside of them. But if you take a look at the same image using something like the Spitzer Space Telescope, which looks in the infrared, what you find is all the star-forming regions that were previously obscured by dust that lie inside the spiral arms. And equally important, you can actually detect the emission coming from the material being heated by the central supermassive black hole. And so what this tells us is that if you're going to be studying the bulk of the star formation and the black hole growth rate across cosmic time, in many cases, all of this key information will be obscured by dust. And so the best way to study these objects is by looking at their spectral energy distributions, particularly in the infrared. And so when I think about star-forming galaxies, I typically think about both main sequence and starburst galaxies. Now, in the optical, they might look very similar, but their key differences lie in the mid to far infrared. And particularly, starbursts tend to be a lot hotter than their main sequence counterpart. And the reason for this is because starburst galaxies are undergoing an intense period of star formation. And what that means is that all of that stellar photospheric emission is going to be radiated outward and reprocessed into the infrared. Now, other galaxies that I think about are elliptical galaxies, which I will use interchangeably with the term quiescent. And the reason for that is because these galaxies are no longer forming any stars. And if they are forming stars, they are doing so at a rate many orders of magnitude lower than their main sequence counterparts. And the thing that's special about these elliptical galaxies is that their SED is in fact dominated by the old stellar population and not the formation of new stars. And the last galaxy I'd like to talk about is the ultra-luminous infrared galaxy. And these are characteristic of having a peak in the far infrared that's coming from the starlight being reprocessed into the infrared, but also an additional contribution coming from the central supermassive black hole that is heating the dust that surrounds the central AGN. And so what this is telling us is that the type of galaxy that you're looking at is going to be determined by the shape of the SED. And so to kind of drive the point home of why we're interested in the far infrared to begin with, if you look at the star formation density across cosmic time, as shown by Mandel and Dickinson in 2014, you find that if you only use UV traces for the star formation rate, you actually underestimate the star formation density. And you can only recover that once you start looking in the infrared, because oftentimes star formation is obscured by dust. Now, equally important, if you look at the AGN luminosity density, you in fact always underestimate the total AGN luminosity density when looking at unobscured type 1 AGN. And in fact, you could only actually recover this when you look in the infrared and recover some of the dusk obscured AGN, which are And so another important thing in the study of extragalactic astronomy is the idea of the galaxy number counts. And oftentimes these galaxy counts serve as a bridge between both theory and observation. And the way galaxy counts works is you first present a set of assumptions on how you believe galaxies form and evolve across cosmic time. And then you populate your theoretical framework with a bunch of galaxies, which, like I said, are characterized by the shape of their SED, but you make an additional assumption on how you believe a singular SED will evolve across many different redshifts. So here in the middle, we're looking at the exact same SED as seen through many moments in cosmic time. And then what you can do is, you combine those two assumptions, and what you can get is the prediction for the galaxy number counts in particular filters in observations. And so if we look at a study from Popovich et al. From the early Spitzer data, when the MIPS 24 micron counts came out, what they found is that when they compared all of their counts to the theoretical models in the literature, they found that none of the models were actually able to reproduce the observed MIPS 24 micron counts. And so what this is telling you is that perhaps maybe your assumption of how galaxies form and evolve across cosmic time is incorrect, but equally important, maybe their assumptions about the SED or the spectral energy distributions were incorrect. And so here on the left are the Insergo number counts, which simply tell you the number of galaxies that are at or brighter than a given flux density. And sometimes it's a little hard to see the differences. So usually we look at the Euclidean normalized differential counts that are shown on the right. And you can see the variation in all of the predictions from the theoretical models. So on the topic of that SED, a study done in that same year by Lagashi et al. In 2024 went back to the spectral energy distributions, and they realized that they were underestimating the role of the features found in the mid-infrared region, particularly the PAHs, or the polycyclic aromatic hydrocarbons. And by making no modifications to their underlying model and only making small adjustments to the SED, what they found is that they were actually able to recover all of the observed Spitzer MIPS 24 microns by only making a modification to the SED. And so the thing I'm going to talk about next is how are the actual current modeling frameworks doing against the JWST MIRI number counts. And so, of course, JWST has been one of the most revolutionary things to happen in extragalactic astronomy, providing us with the most unprecedented data access to the mid-infrared. So having things like better spatial resolution, higher sensitivity, and allowing us to probe deeper than ever before. And so the nice thing about the MIRI instrument is that it probes the 5 to 28 micron, or that mid-infrared region. And the mid-infrared region is characteristic of these PAHs, which oftentimes the strength of the PAHs serve as star-forming or AGN tracers. So in the top right, you're looking at the spectral energy distribution of a star-forming galaxy shown in black. But in the presence of an AGN, oftentimes these PAHs get suppressed, and what results is this rising power law SED. And another thing that's going on is that there have been many multi-band, multi-field imaging surveys. And so the nice thing about this is that we collect photometric data across many different filters in the mid-infrared over many different fields. And so what this allows us to do is to perform spectral energy distribution fitting across from the UV to optical, infrared, and far infrared. And what this is going to do is allow us to disentangle some of the degeneracies that had existed in the literature, allowing us to get physical properties for things that were previously dust obscured, like dusty galaxies or dust obscured AGN. And so I want to highlight a key survey in particular called the SMAUS survey that was led by none other than George Righi himself. And in a particular AGN study that came from that SMAUS survey, what was found was that more AGN were being discovered than previously predicted. And so here you're seeing the integral number counts for the total galaxy shown in gray, and the AGN contribution of different types is shown in colors. Now, the other big thing is that the AGN tended to dominate the bright end of the number counts. And this particular filter is at the 25.5 microns, which starts to approach the far infrared. And what's really interesting about this is that a lot of the far infrared models don't actually account for AGN because they assume that they do a marginal contribution or perform no contribution to the integral number counts. And so another puzzling result that came out of this John Way Leo paper in 2024 is that they found that the obscured fraction of AGN seemed to increase with increasing AGN luminosity. And this was contrary to the results of a study done by Mark Lacey et al. In 2015 using Spitzer data, where they found that the AGN obscured fraction would decrease with increasing luminosity. And so what we want to do is we want to go back to the models and to see how we're doing against current observations. And so on the empirical side of things, this effort has been largely led by Rowan Robinson since the early 2000s. And essentially what he does is he starts from the evolving 16 micron luminosity function. And then he adds on things like observationally driven SEDs for 5 different galaxy populations. So adding things like quiescent galaxies, starbursts, post-starbursts, and an AGN dust torus model. And by doing this, you can actually reproduce some of the observed counts that were seen at the shorter wavelengths, such as the 5.6 micron MIRI counts. Now, another model that's been really popular in the PRIMA community is the SPRITZ empirical model. And the thing about SPRITZ is that it creates mock catalogs by sampling from the Herschel luminosity functions for their respective galaxy populations. And so the nice thing about SPRITZ is that it actually includes the nebular emission coming from both star formation and AGN, which means it's particularly powerful for making predictions in the far infrared. And it's been used most recently to test against some of the black hole growth rates across cosmic times assumptions. And it's being used a lot for PRIMA studies. So it's really exciting to have this model for comparison. Now, how does it do against the observed JWST micron counts? In the study done by SMILES, they found that they were able to reproduce the 7.7 micron counts. Now, how are the semi-analytic models, or SAMs, doing at predicting the JWST number counts? So SAMs start from these dark matter simulations, and they use the halo merger histories to tack on some analytic prescriptions on how galaxies are believed to evolve across cosmic time. So you can add things like gas cooling mechanisms, star formation, feedback processes coming from both AGN, and metal enrichment processes coming from supernova. And by doing this, you can essentially construct these light cones, like, for example, most recently, the Santa Cruz semi-analytic model creates these 3-dimensional light cones that create mock observations. And in particular, the Santa Cruz SAM is really powerful because it's been well tested against all the different observations from the UV to the optical, and been tested has been tested super into higher redshifts. And so if you take a slice of this light cone here and project it on the 2D space, what you can see is that you can actually reproduce some of the clustering effects that you actually observe. And each of these little dots here represents a singular galaxy, but better yet, hosts a whole myriad of physical galaxy properties. Now, other SAMs in the literature include the ones presented by Cowley et al., which was really popular because it was one of the leading frontrunners for predicting some of the JWST MIRI number counts. And most recently, the SHARC semi-analytic model presented by Claudia Lagos et al. In 2018 has been making a lot of headlines because their original intention was to incorporate AGN into the number count predictions. And so a lot of those papers on modeling the AGN properties have been coming out most recently. But how are the SAMs doing at the actual comparison with the JWST observations? So in the early release science from Sears, a variation of the Santacruz-Sam and the Galfer model from Kelly et al. Was tested against the observed 5.6 micron counts. And what they found is that they were actually overestimating the contribution of the galaxy counts at the faint end, and in some cases under-predicting the galaxy counts at the bright end. But of course, galaxy counts are only a first order test. The number of galaxies you detect won't actually tell you anything if they're not representative of the distribution of galaxy populations you actually observe. And so the Cowley model, we took a closer look into it, and what we found is that in their 2018 paper, in blue here was their predictions for the total galaxy number counts, but this dashed green line, which you can barely see, actually represents the quiescent contribution, which means that the quiescent galaxies were actually expected to dominate the galaxy number counts, in particular for the MIRI F560. But in a study done by a Tufts undergraduate, Leo Saikov, back in 2024, he did a comparison of the source properties of the MIRI F560. And what he found is that when he compared the star formation rate as a function of stellar mass and overlaid some of the main sequence observational constraints presented by Koprowski et al. In 2024, what he found is that, in fact, actually the dominant population was main sequence galaxies. And there was some quiescent galaxies, but not at the level that was predicted by Cowley back in 2018. And so what this is telling us is that theory and observation are a feedback cycle. So oftentimes theory presents a set of assumptions that oftentimes gets challenged by new and recent observations. And so we as theorists have to go back to the drawing board and to see where we fell short. And so at this point, I think it's a really good time to introduce what it is the FIRESIDE project is. And so FIRESIDE stands for the Far Infrared Extragalactic Survey and Instrument Design, and is being led by our wonderful PI, Vivian Yu, who's in the audience today. And so here you can see some of the other collaborators that are working on a lot of the FIRESIDE projects. And so the motivation behind FIRESIDE really came from the community itself. So following the Astro 2020 Decadal Survey, and most recently the NASA Precursor Survey, the community had highlighted a lot of gaps in far infrared science, some of which are shown here on the left. So things like the role of source confusion in far infrared imaging surveys and the need to disentangle the role of gas and dust on the coevolution of supermassive black holes and their host galaxies, particularly at high redshifts. And so in response, the FIRESIDE project was created with the intention of being mission agnostic, but with PRIMA hopefully underway, products that are useful for both the far infrared and PRIMA community. And so here's kind of an overall schematic of what we're doing at FIRESIDE. And so what we're doing is we're taking this multi-pronged approach using both semi-analytic and empirical methods to build realistic realizations of the far infrared sky. And then we're going to run these outputs through fancy software tools to tailor them for the uses of PRIMA. But you can imagine that you can also tailor these broadly to explore the instrument parameter space. And then so what you get as outputs are these mock galaxy catalogs that include AGN, but more importantly, contain different spectral emission line features that are very useful for those who are interested in survey and instrument design exploration. And so what I'm going to do now is highlight some of the key projects that are being done at FIRESIDE right now. And so the first person I'd like to highlight is Pallavi Patel, who is a postdoc at JHU. And what she's doing is incorporating AGN to cosmological simulations. In particular, she's using the SIMBA hydrodynamic simulation, which includes things like black hole growth, feedback mechanisms, and most recently, a dust treatment. And then what she does is she grabs a representative sample and doing things via post-processing, models the gas and dust emission processes using things like radiative transfer tools such as PowerDay and SLIC. And so these tools are really awesome because they allow us to model the nebular emission coming from a range of sources, such as diffuse ionized gas, H2 regions, and now even AGN. And so here's an example of a schematic on how we run the radiative transfer modeling, and particularly for the SLIC model. So you can imagine that each of the outputs from the SIMBA galaxy can be represented by a collection of many gas particles. And we can imagine that those could also be represented at different gas clouds, which get illuminated by a variety of different sources. So things like nearby stars, the interstellar medium, cosmic rays, and so on could contribute to the illumination of these gas clouds. And then what SLIC does is it runs a multi-zone model for each of the gas clouds to estimate its light luminosity. And then you can just sum over all the different contributions, sum over all the different gas clouds to get a total emission line luminosity. Now, the important thing here is that we want to add an AGN contribution and to see how the activity of the AGN affects the emission line luminosities that we see. And so in a preliminary study, what we found is that we were actually able to reproduce both the C2 luminosity as a function of both star formation rate and infrared luminosity. And these were compared against an observational sample seen at cosmic noon or redshift 2. But the only caveat here is that we didn't find a dependence on the AGN yet. So we're currently actively working on updating that AGN framework to include a more realistic radiation field-like source. And eventually down the line, you can imagine we could explore the parameter space and include things like AGN fraction, obscuration, and even what the merger state is. Now, on the empirical side of things, an effort being led by Justin Cater is on modeling the infrared luminosity function. And so way back then, it was discovered that these objects known as protospheroids dominated the sub-millimeter galaxy counts, particularly at these high redshifts. And so back in 2013, Kai et al. Gave us a powerful hybrid modeling framework to model the evolution of these protospheroids. But in addition, it provided an AGN contribution that was allowed to co-evolve self-consistently with the protospheroids. And in fact, it was actually able to reproduce a lot of the observed luminosity functions. But of course, all of these models were calibrated pre-JWST data, and since then, JWST plus more recent ALMA observations have improved the constraints on the properties of gas and dust and AGN. And so what we want to do going forward is to kind of go back to the models and kind of recalibrate them with new and updated information. Now, something else that Justin is super interested in is on constraining line luminosity functions. And so in the literature, there are many examples of far-infrared line continuum relationships that use a lot of different galaxy samples and AGN. But the problem with these samples is that they're oftentimes very heterogeneous and don't take into the account the effect of selection. So some of these might have some contamination from dusty galaxies, and we actually don't know how they manifest in the line luminosity relationships that are outputted. And so the goal now is to use a photoionization model such as Cloudy to see how the gas responds in the presence of various radiation sources. So this will tell us, for example, what we expect the emission line luminosities to be for a given ionizing source with varying properties such as melodicity and gas contact. And so the idea here is to provide a set of empirical line luminosity relationships, which can serve as a sanity check for some of the radiative transfer modeling done by Pallavi. And so that's kind of like an overview of what we're doing on the empirical and radiative transfer side of things. And I trust that these people would correct me if I said anything wrong. But now what I'm going to do is transition to some of my more recent work, which takes a semi-analytic or semi-empirical approach. And so the way I'm going to do this is by using something called pySIDES, which is the simulated dusty extragalactic sky Python code that was written by Matthew Betherman back in 2017. And so the way this works, it's very similar to its semi-analytic counterpart, but it has different assumptions on how it constructs galaxies. And so we always start with a dark matter simulation, and we populate the halos using a technique known as abundance matching. And what we want to do is we want to reproduce things like the stellar to halo mass relationship. And then if we want to have some physical properties, what we can do is we can tack on some empirical prescriptions and sample from the observed stellar mass function, or for instance, the fraction of star forming to quiescent galaxies that we see as a function of both redshift and mass. And by doing this, we can tack on a list of physical properties to each of these dark matter halos. Now, to generate some observed fluxes, we can tack on some dust emission templates, such as main sequence and starburst templates. And in particular, the pySIDES model does include quiescence, but they're assumed to not emit in the far infrared. And that makes sense because a lot of these quiescent galaxies are, in fact, dominated by their old stellar population. And so optionally, if you really wanted to, you can include some information about your telescope, and the final output is this pySIDES semi-empirical model. And here's a logo of the SIDES model. But if you squint your eyes and look closely, what you realize is that this is one of the many realizations of the output of the SIDES semi-empirical model. So each of these dots that you see on that logo represents a single galaxy with a whole list of physical galaxy properties. And of course, since this was all calibrated in the far infrared, it's actually able to reproduce a lot of the far infrared properties, such as the galaxy number counts. Now, more recently, back in 2022, Matthew Betherman added some spectral emission lines. So now we're actually able to model some of the continuum emission lines, the CO, the C1, and the C2 emission lines. And a lot of these things were constrained using some of the more recent ALMA observations. And just this past year, the SIDES model was used to actually test the source confusion limits for the PRIMA imager. And so what is the motivation behind my work? So what I really wanted to do is take this semi-empirical model that is well calibrated into the far infrared and extend it down to the mid-infrared while also including some of the missing populations. And so what I wanted to do is I wanted to include things known as AGN, but not only that, I wanted to include things known as self-forming AGN composites. And the reason for that is because a lot of models in the literature assume a single AGN template. And by doing that, you kind of ignore the continuum of AGN sources that are modeled by their AGN fraction or their AGN strength. Now, in addition, SIDES has the flexibility of being able to be fed in any arbitrary light cone. And since the Santa Cruz SAM was calibrated well in the UV to optical, we wanted to see if we can get some dust emission properties from the Santa Cruz SAM by feeding it into the SIDES model. And then the last thing we want to do is wanted to see how our models did against the new recent JWST number counts. And so the first thing I had to do is I had to modify the SED templates from the SIDES semi-empirical model. And so the templates come from the Magdis et al. Dust emission templates which model both main sequence and starburst galaxies. And these are shown on the right here in color. And the color here represents the mean intensity of the radiation field, which is a parameter that is closely related to dust temperature. But now, since I'm observing in JWST MIRI, you can imagine that at these shorter wavelengths, as you increase the redshift, you're actually going to be sampling from the stellar emission, particularly the 1.6 micron stellar bump. And so what we wanted to do is we wanted to introduce a dust emission template which scales with LIR, or infrared luminosity, and a stellar emission template which scales with mass. And the last thing we want to do is we want to actually model the quiescent galaxies. And so what we did here is we used the elliptical 5 galaxy template from the Swire template library. And this is a template that has a mean stellar population age of 5 billion years. Now, the big thing I actually really cared about was integrating AGN SED library into the SIDES semi-empirical model for a range of sources characterized by their AGN strength. And so what I did is I adopted the SED template library, the mid-infrared AGN library from Allison Kirkpatrick et al. Back in 2015. And so these SEDs are really special is because they are made and constructed using Spitzer IRS data. And what that means is that a lot of the mid-infrared features, such as the pHs, we believe are going to be really constrained really well and be representative of the observed samples that we see. And the only modification I made to these templates is added the stellar contribution, just in case I was sampling at higher redshifts at the shorter wavelength of the MIRI instrument. And so here is the final SED library that I get. And so these SEDs are characterized by something known as the AGN fraction, which I define as the ratio of the AGN infrared luminosity over the total infrared luminosity, which has contributions from both star formation and AGN. And then just for some definitions, I'm going to define something known as a star-forming galaxy. If it has an AGN fraction of less than 0.2, things are going to be star-forming AGN composite for things that are between 0.2 and 0.8, and anything that's AGN dominated will have an AGN fraction greater than 0.8. And so the only tricky part here was actually determining an AGN fraction for my simulated galaxies in the SIDES semi-empirical model. But the nice thing is that we do have a well-tested Santa Cruz SAM analytic model that has been well-tested from the UV to the optical. And so what this means is that we can use that to inform size of incorporating AGN. And so the Santa Cruz SAM has this parameter called the black hole accretion rate, which means we can essentially model an AGN disk luminosity, which is characterized by its radiative efficiency, epsilon, its black hole accretion rate, m dot, and scaled by c squared. And then we make an assumption that some fraction of this disk luminosity is going to be reprocessed into the infrared. And so for the most heavily obscured system, an alpha value could be anywhere between 0.8 and 1. And for type 1 AGN, which are typically unobscured, this value could be anywhere between 0.2 and 0.3. And so the way we actually do this is that we construct probability density functions for the AGN fraction for all of the sources in the Santa Cruz SAM. And we do this in bins of both infrared luminosity coming from star formation and redshift bins. Now, the problem here is that if you want to sample from this, arbitrary distribution, that would be a complete nightmare to do. And how do you actually model this? But what you can do is you can use a fancy trick known as the inverse transport sampling procedure. And what that allows you to do is essentially construct the empirical cumulative distribution function, and then you can generate a number between 0 and 1 and map yourself onto the ECDF, and then finally project yourself down to the AGN fraction. And by doing this, I essentially was able to probabilistically inform the sides model of an AGN fraction. And now, after doing those small little modifications to the pySIDES model, how does it actually do against the new observations from JWST? And so here, what I'm going to show you is 8 different panels corresponding to each of the 8 broadband filters that are on board the JWST MIRI instrument. And all these markers here correspond to some of the observations that were done by various imaging surveys. And in dashed blue are the results from my new updated pySIDES model. And what you can see here is that across all 8 filters, I'm actually able to reproduce the galaxy number counts. Now, of course, like I mentioned earlier, galaxy counts are only a first order test, and they're only as good as as how representative they are of the galaxy populations you observe. So we can look at things like the redshift distributions, and here I'm showing you again for all 8 different broadband filters. And in black will be the total redshift distribution, and the colors here will represent the contribution by different galaxy populations. And now the key takeaway here is if we look at this orange line that is, at the very bottom of all these redshift distributions, this corresponds to the quiescent galaxy contributions. And what you see here is that at neither of these broadband filters are the quiescent galaxies ever dominating the redshift distribution. And this is contrary to the results that was presented by Kelly et al., but it aligns with the recent observations presented by Leo Saikov in 2024. Now, on the topic of galaxy population counts, we can also take a look at the AGN counts because John Wei Leo provided that for us. And so here, what I'm going to show you is again those 8 different broadband filters. In dash is going to be the total galaxy number counts, and these markers would represent lower limits on the AGN number counts detected. Now, if I overlay the AGN contribution to the total galaxy counts, you find that I'm able to only reproduce the observed sample at the brightest end, and that I actually underestimate the role of AGN on the total observed galaxy counts. But if I introduce things like my star-forming AGN composites, and better yet, their combined contribution, you find that across all of these 8 different wavelengths, I'm actually able to reproduce the observations that we're seeing across each of these 8 filters. Now we can do a fun exercise and divide those by the total number counts to get these population fractions. And if we zoom in at the most important features of these plots, we find that across all 8 different filters, we're actually able to reproduce the AGN fractional contribution to the total number counts. Now I'm going to switch over to the idea of cosmic variance. And if you've been working with MIRI, you know that the most frustrating feature about MIRI is that it has a small field of view. So you're always going to be dealing with the effect of cosmic variance, which means you're going to be probing over or under dense regions of the cosmic web. And so here what we're looking at is the galaxy number counts that were observed by MEGA, and they're overlaying some of their total number counts as seen through various different pointings. And so you can see here that the number counts can actually fluctuate by a factor of 2 depending on where you're looking in the cosmic web. And then, so what I did is that I was looking into the study done by our Tufts undergrad, Leo Saikov, and what he presented was some of the source properties for the galaxies observed in MIRI F560. And here he's showing the redshift distributions, and I was kind of curious to see if I could actually reproduce the observations. And so what I did is I took my light cone and I subsampled it to recreate the observational strategy in this work. And then I find if I do this over 5,000 realizations, I'm actually able to, in fact, recover the redshift distributions. So in solid blue, you can see the total redshift distribution, but the filled-in region represents the 1 sigma uncertainty. Now, the other thing that we were interested in is quantifying the effect of cosmic variance on bright AGN sources. And so we know that AGN are rare in cluster, and the number of AGN detected, the uncertainty on that value decreases with increasing survey area. And so if I repeat that subsampling procedure, but only this time increase the survey area sampled, I'm actually able to reproduce that trend. And each of these lines here represent the fractional error or the uncertainty in the observed number counts for bright AGN in various different flux limits, particularly at the F1500. And so the key takeaway here is that even flagship surveys like SMILES will suffer from cosmic variance. So the SMILES survey in particular has anywhere between 20 and 30% uncertainty on their observed AGN samples. And so going forward, what we're going to advocate for is that all surveys should have at least an area of 150 arc minutes across multiple different fields to minimize the uncertainty there. And thankfully, Minerva, maybe something you've heard about, being led by Adam Muzzin, is collecting over 250 squared arc minutes of parallel pointing which is going to provide us with better constraints on the number of AGNs that we detect. And so just to kind of summarize the key takeaways behind my recent work, I essentially updated the SCT template library for the pySIDES semi-empirical model and included things like an AGN SCD library that's modeled by the AGN string. And by doing that, I find that I'm not only able to reproduce the observed number counts, but I'm actually able to reproduce the contribution of the AGN counts and even the fractional contribution of the AGN. And then I found that I was able to reproduce a lot of the redshift distributions that were seen in MIRI F560, and I quantified the effect of cosmic variance for bright AGN sources. And so at this point, I think I want to talk about the future work and how we can adapt our modeling framework for the interest of the far-infrared community and PRIMA. And so what we're going to do, the first order thing to do, is to compare some of the outputs from the empirical and radiative transfer approaches that are being led by Justin and Pallavi, and compare that with their outputs from pySIDES. So we can compare things like the C2 luminosity as a function of both star formation rate and infrared luminosity, the AGN luminosity function, among other things. And the idea here is that we hopefully have 3 independent approaches that converge onto the same results. And the nice thing about pySIDES is that it's super modular and flexible. So depending on the recipes that come out of these empirical and radiative transfer approaches, we can tack them into pySIDES and let the user be free to choose whatever recipes they really trust and are most comfortable with. And so the hope is that we're going to add a lot of the mid-infrared and far-infrared tracers of star formation in AGN. And so that if we have a model that's well calibrated in the mid-infrared, you can imagine that higher redshift, some of these sources will fall in the vicinity of PRIMA. And this will be super exciting to make predictions for PRIMA because, once the new data comes in, we can actually challenge, the theoretical framework that are presented here today. And then the last thing that we're doing is survey and instrument design exploration. And this effort is being led by Carl Ferkenhoff, who's a professor at Winona State University. And essentially what he's doing is he's taking the outputs of all of our simulated catalogs and adding on things like a point spread function, instrument filters, performing source extraction. And he's going to do this via a user-friendly web page so that anyone in the far infrared community could come in, present their set of their set of telescope systematics and survey instrument design, and then output some predictions. So some predictions would be really useful for PRIMA, but it doesn't just have to be PRIMA. It could be anything of your choosing. And so, that's pretty much concludes the end of my talk. So I'd like to just quickly advertise that FIRESIDE is currently actively working on a lot of products for both the far infrared and PRIMA community. And so I kind of want to welcome you all to join our monthly FIRESIDE chats. And you can reach out to me or Vivian on joining this. And so in that monthly chat, we just talk about far infrared science and some of the updates on our theoretical modeling. And lastly, the paper actually just came out on arXiv this morning. So if you're interested in more details, you can always click the link there and to learn more. But I'm happy to take any questions at this point. And thank you all for your time.
Wow, thank you so much, Edgar. That was a really great talk and very interesting. Would love to open this up now to folks on the call with any questions for Edgar. Feel free to either post in the chat or go ahead and just unmute yourself and whatnot. Okay, cool. We have a question from Matt Malkin in the chat, so I'll just read that out right now. Matt asks, so you assume that at high redshifts, there's the same amount of dust in AGN as at low redshift and the same number of heavily obscured AGN. Do you want to comment on that, Edgar?
Yeah, it's a really great question. I think the interesting thing about that question is that a lot of our AGN SED templates were calibrated with Spitzer IRS data at cosmic noon. So I guess you're right that in fact that we are making an assumption that the dust properties at cosmic noon and below are the same at high redshift. So I think it'll be really interesting once those high redshift sources come out to compare those with the observations and see where we need to recalibrate. Because right now it is an assumption, but we can always go back to the modeling framework and update them. Yeah, but that's a really good question. Thank you for that.
Anyone else want to ask a question? Edgar, one thing I'm curious about is, PRIMA would be transformative in terms of wide area mapping of galaxies that are in like the types of things that these number counts are really picking up. And so I guess I'm curious as to how much you've thought about what adding spectra on top of all of this does. Uh, have you thought about that at all?
Yeah, so I guess for spectra in particular, I think what Carl was telling me is that, depending on what observational strategy you choose, you can actually get predictions for what emission lines you'll actually detect. So the most
Mhm,
popular ones are like C2, CO, and C1. Those are the
mhm,
most popular ones, but there's also other ones like the oxygen 4 line.
mhm.
So that way, when you do your proposals, you can actually, generate some mock observations and be like, okay, so I'm going to propose, this for, I'm assuming Prima has a general observers program so that you can
Yes.
use the mock catalogs to kind of inform the proposals that you're working on. And since it's super wide area, that's like super exciting because we're going to minimize the effect of cosmic variance. So that's something I'm really looking forward to if that actually happens.
Yeah, definitely. I guess one interesting thing to do would maybe be to dig into some of these different models and look at if there are different, if there's some predictive power based on the line like map predictions.
Yeah,
Um, Gotcha.
yeah.
Presumably with some of the higher ionization far infrared fine structure line tracers that might be really booming in some of these AGN that you've been talking about.
Yeah, of course, of course.
All right. Does anyone else have any last questions for Edgar?
Maybe I'll just quickly chime in and say, sorry, I couldn't figure out how to use clap on Teams earlier, but that was a really good talk there. I'm a little biased, of course. But yeah, and then I think that it'll be good. It's sort of in our thinking that we would also kind of use cloudy to kind of build up some kind of photonization grids to understand what we may be getting once we get the PRIMA sensitivity to the lines and what it is that we're really seeing. So I think all of that will fall in the same place. And I'm personally very interested in the spectroscopy as well. So that's a good piece I'm really looking forward to with the PRIMA surveys. So sorry, it was more of a comment and a question, but
No,
yes.
it's
Excitement.
fantastic.
Yes. Yeah.
Thanks for chiming in, Vivian, definitely.
Yeah.
All right, great. Well, if there are no other questions going once, twice. Okay. Well, just please give Edgar a virtual round of applause one more time for that great talk. Very impressive for a second-year graduate student. Thank you so much for that, Edgar. This was really awesome. Looking forward to the work that you're going to be doing in the future. Definitely check out Edgar's paper. I was flipping through it this morning. Very cool plots. And we hope to see you back in about a month. Just a reminder that our next show will be November, or our next peak cast will be November 17th. And we are planning a large PRIMA presence at AAS. So hope to potentially see some of y'all there. But thank you for coming. Thanks again, Edgar, for your wonderful talk. And see you next time, folks.